So today, good morning. Today we'll have a lecture on mass spectrometry. So I'll first tell about the principle of mass spectrometry. The basis of mass spectrometry is the production of ions from the neutral species or neutral molecules and the examination of these ions, the composition of those ions. So I write down here the basis of mass spectrometry is the production of ions. Spectrometry is the production of ions ions from neutral species or neutral molecules, neutral species or molecules, and the study and examination, or you can say, and the study or examination of the subsequent decomposition of the ions, decomposition of ions Okay. So here, so I'm looking at the basis of mass spectrometry is the production of ions from neutral species or molecules and examination of the subsequent decomposition of these ions. So here in the mass spectrometry, so this is neutral molecules or species is bombarded with high energy electrons. So it can have two types of systems can come. So when the molecules are bombarded with high energy electrons, so it can have two types of species can be formed. First one is anion radical, and second one is cation radicals. In the first case, when the high energy electrons bombarded, the neutral molecules pick up trap the one electron, so it gives a negative charge anion radical. In the second case, the high energy electron knock out one electron from the neutral species, so it gives two electrons, one knock out from the neutral species, so to get the positive charge, so it is called cation radicals. So you have two types of species can be probable when neutral molecules are bombarded with high energy electrons. So you can have anion radical where the electrons are trapped by the neutral species, and another one is cation radical where one electron is knocked out from the neutral species to give the cation radical. This cation radical can undergo further decomposition. So mostly in the mass spectrometry, this type of formation of cation radicals and their examine subsequent decomposition of the ions takes place. So here I write down again. So when high energy electrons, so we got cation radicals from, so first, so this neutral species bombarded with high energy electrons, so we got cation radical. Okay, this cation radical are generally known as molecular ion, in the molecular ion, or you can say or parent ion. Okay, parent ion. This parent ion can undergo further decomposition or further fragmentations by bombarding with high energy electrons. So it can have, say, let's say M1 plus M2, M1 cation radicals, another one neutral molecule, or you can have M1 positive charge plus M2 radical. Okay, so you can decompose like this. So this known as decomposed ion or fragment ions are known as fragment ions, or you can say or daughter ions. They are known as daughter ions. So then the neutral molecules bombarded the energy, and the energy they get molecular ion. This molecular ion can undergo further fragmentations by this energy, electron energy. So this again can bombard, so it can give so on another set 3 or M4 like this, one electron neutral molecule, or you can have M3 positive charge, M4 like this, so on. So you can produce another system like this, so you can go so on. So many fermentation can undergo. So in the mass spectrometry, the study of these ferment ions, like the ions, these are the ferment ions, these are ferment ions, this is also ferment ions, this is also ferment ions. So they are all studied together in the mass spectrometry. Generally positive charge and catalyticals are studied. So it is about the principal mass spectrometry. Now I will give some examples, see how the electrons are knocked out from the neutral molecules. So let's say benzene. Benzene has this is neutral benzene, okay, neutral species. Benzene has structure of benzene. Okay, we know about with high energy electrons, when it is bombarded with high energy electrons, benzene can give fast and say one electron is here, one sorry here, no, like this. So one here, so let's say this is a benzene reticles, these are the benzene molecules, neutral molecules, they have two electrons are here. So why? By bombarding with high energy electrons, so one is removed, no out this one electron. So it gives two electrons here. So it gives a pair, this is called molecular ion, or you can say parent ion. So you can write this like simply like this one. So you can write this like this. Or you can write like this also, like this. Okay, this way, what I'm telling that here these double bonds have two electrons are here when high energy electrons bombarded. So one electron is no out, so you can positive charge here. So you can write this way, or another one here, so here like this. Or you can say this M plus ion. So this is another parent ion or molecular ion. Similarly, you can have many examples here. Say here double bonds. So also you can have in double bond or amines like this. In double bond, so you can have this positive electrons, then you can have one positive charge, this one electron lower from here, so you got a one like this, or you can have this C double bond C, this one can represent this way. So this is the parent ion, or you can say molecular ion. Similarly, you can have many examples. Sorry, alcohol also you can have alcohol. Is here, so electrons, whatever one electrons will knock out, so you can have a positive charge, and O is like this. So these are molecular ions. So you can have simply you can write ROIs. So this is the molecular ion or parent ion. So similarly amine also you can have. So let's say this hydrogen or N is okay. Amines are like this. So you can knock out with the electrons. Bombarded with high energy electrons, so you can have this parent ion or molecular ion. Suppose to start here like this, so you can have this one. So you can write this way R C A and so on as like this. Okay. So this way, these are can be represented by this way or this way. This simply you can write all molecular ion. Okay, simply represent like this. So these are all bring carbonyl also you can write carbonyl. Okay, so you know about one electron, so you can give one electron with this charge here like this. So you can have also this can be given this way. You can have this way also given by this. So you can have another regional structures. So two electrons are given here. So you can have this another positive charge here. So you can have positive charge, or I will write this. Okay. Similarly, you can write. Okay, suppose you know this one. First step is formation of this one electrons of oxygen. Then you can okay, this way. Okay, so you got this one. You can have carbonyl. Okay, like this. Or most generally you can have this can have one electron like this, so can get one like this, go one electron, or one electron can go this way. So you can have another structure. You can have carbon positive charge and then oxygen, and this one electron, one more electron coming up. So you can have here. So this two electrons are coming here. Okay, like this, two electrons are coming. So here two electrons. So here you can have two electrons and one here. These two electrons are here and one electron here. So you can have this also positive charge here. So you can same way. This is same way. or equivalent. These two are equivalent. So you can write carbonic acid. Positive charge can be either in the oxygen or in the carbon. By the resonance, you can get in the carbon cation or in the oxonium ion. So these are all studied. So I'm giving examples of how the positive and parent ion or molecular ions are obtained. So by bombarding with high electron energy. So they can undergo further, these molecular ions can undergo further uh, decomposition or fermentation to give the other ions. So in the mass spectrometry, so we studied these fragment ions and the molecular ions by bombarding the stellar species or natural molecules with high energy electrons. So in the high energy electrons are mostly that's like around 70 electron are used. 70 electron are used so that they can decompose mostly organic compounds or covalent compounds, covalent bonds, or mostly can be decomposed by this method. So in the mass spectrometer, the each positive charge or this are obtained from the molecular ion positive charge cation radicals are measured by mass to charge ratio, or you can say mass to charge ratio. Okay, so determine charge ratio. So m by e, or where e or z is charge, m is the cursor. So by knowing the molecular ion peak, we can know the molecular mass of the compound, because charge is mass of the charge is very, electron is very less, can be minimum. Okay, actually minimize on its head. So mostly m by value of the molecular ion is the molecular mass of the compound. You can say like that. So if you now say that this is a molecule bombarded with electron, so you got a cation radical, the molecular parent ion, so this is m by z value we calculated. So that this is m by z value is same as the molecular mass of the compound. So by knowing the m by z value of this molecular ion, we can know the molecular mass of the compound. And again, can undergo further fermentations, say M1, M2, and so on. Okay, so you can have cation radical or neutral molecule, or you can have cation positive charge and then radical. So these are all cation. So these fragment ions can be studied M by Z value, or these fragment ions can be studied together. So by knowing the most of fragmentations and M by Z values, we can know the structure of the compound. So this is the principle of mass spectrometry. So in the mass spectrum, so M by Z values are plotted. So in the mass spectrum, I'll give here, okay, I will write down. The mass spectrum, the M by Z value are plotted against the relative abundance of the compounds. So mass spectrum. So in the mass spectrum, okay. So here M by Z value are plotted M by Z value. Go along the abscissa, along the abscissa, and the relative abundance, you can say relative abundance, abundance is along the ordinate. This is along the abscissa. By knowing this, so here you can pick to be like this. This is a 0, 100. Relative with 100, 50, okay, 50. So here, so peak will be like this, or sometimes like this, or like this. High intensity 100 is like this, so like this. So mass spectrometry is studied along the M by Z value, along the abscissa, and relative abundance is along the ordinate. So what is the relative abundance means? Relative abundance is the relative abundance is the percentage of the iron current. That means the highest will be the 101. So relative to this, all the peaks are relative to this, the highest one. We have calculate the percentage abundance of this compound. Okay. So here, I'm repeating again that mass spectrometry is a record of the mass and the relative abundance of the mass to charge and the relative abundance of the molecular ion and positively charged fragment ions formed by it along by the electron moments. So the M by J ratios are taken along the abscissa, along the abscissa, spelling is abscissa, and the elective evidence is along the ordinate, ordinate, okay, ordinate. So elective evidence is along the ordinate, and the M by zero ratios are taken along the abscissa here this way, like this, and the relative impedance is the means the percentage of the metal ion current. That is the cathode current more abundant of the ions. So here generally molecular ion peak M plus ions has the highest peak. So the highest peak. If the relative impedance is 100%, then it has to be base peak. So generally base peaks are the molecular ions are peaks are base peak, but sometimes they are true also, because mostly having the most currents ion, having more stars, more number of ions are present, then they said to be have base peak. So for example, I will give the example of say, methanol, okay, mass spectrum of methanol. So mass spectrum is a graph plotting against the mass to charge ratio against the relative impedance. Relative impedance is the percentage of the ions present, ion current. More current ions are present, then it is the highest peak. So the highest peak having the 100% will give the base peak. So generally molecular ion peaks gives the base peak, but they are not true. So sometimes okay. So but the value are along the abscissa and the relative impedance is along the ordinate. So I'll give one example for about say, let's say methanol, mass spectrum of methanol. Methanol can undergo fermentation. So let's say methanol, CH3, O is okay. Here, this is methanol. When you bombard with high energy electrons, so you can give one electron is no out. Here, one electron is no out. So you can have say O positive and this hydrogen. So this is the you can say this is the M plus molecular ion. You can write simply CH3O is okay. You can write this way also. Then this can undergo fermentation, further fermentations with electrons. So you can lose one hydrogen ion. So you can lose like this. So you give one electron is given here. So here, another one electron goes like this. So you can have CH3, or you can write this way. Another way you can write this way, or another way. Okay, this is right this way. Okay, I'll write this way. CH3 here, CH3. So here CH2, O. Okay, positive charge is a molecular ion. So you can have this proton can be lost, this hydrogen can be lost like this, and this one can go, and this I can write this way. Okay, this will go. So now you can have, so I write here CH2, double bond here, over here, one and one positive charge here, hydrogen here. So here. So the one this goes on, one hydrogen ion is gone. Okay, radical has gone. Hydrogen radical has left. So you can write plus here. Radicals, formation radical. So you got another value, another fermentation. So this fermentation takes place like this to form this one. Okay. Then again this can clip one. This also clip one. Two hydrogen atom can be clipped from here. Two hydrogen atoms can be clipped, one from here, another from here. Then you can have this can undergo further fermentation. This compound can come out. So C triple bond O. So here positive charge. Okay. Here one hydrogen, two hydrogen atoms are lost, two neutral molecules are lost. So one is given here, another one is given like this. So you can write this way. So you can have another ferment ion. And this molecular ion can undergo further and loss of one hydroxy group. So you can have this loss. So you can have CH3 with this charge plus OH radical, okay, hydroxy radical. So now we have fermentation. This molecular ion can undergo fermentation. So you have molecular mass of methanol is 32. Okay, so M by Z here also 32. So loss one here, these fragment ions can have 31 M by Z value. So here M by Z value 2 are lost. So from here 2 are lost. From here to 29, and this is from M by Z value 15. Okay. So cation or these cation radicals are studied in the mass spectrum. So this I'm giving one example of methanol, how methanol undergo fermentations. So this is an intermolecule of methanol when bombarded with high energy electrons. So you go a molecular ion peak and plus so parent ion, molecular ion which having the M by Z value 32. This M by Z value is same as the molecular mass of the methanol. So then this undergo fermentations will lose one hydrogen radicals to get this one ferment ions, and then lose another hydrogen intermolecule. So it goes another cation radical 39. So you can see how it is ferment from here. I'll show you the mechanism of this CIs. Hydrogen here, double bond. Oh, okay. So here two hydrogen atom will be lost. So here, so positive charge here. So first one will be lost here. This is really lost. Okay. This will be here, another one will be here, and lost like this. So these two will form. Hydrogen will get these two hydrogen radical. So first will be CIs, and then this multiple bond or a positive charge, and this is one hydrogen and two hydrogen radical combined together. Two hydrogen radical combined together, you got this intermolecule. So it is formed like this. Okay. So I'm giving the mechanism how it is formed. So there we got another fragment ion. So let's see the spectrum of this simple molecular ion, how it is formed. Let's see the spectrum of this methanol molecule. So fragment ions we got. So we have mass spectrum of methanol. So here this is the mass spectrum. So it is 0 to 100. Okay, 100. So nearly 50. Let's table at 50. This is relative abundance. The abundance of the then this is the let's say 0, 5, 10, okay, 15, 20, then 25, 30, okay, say 35 here, 35. So let's say this one. Okay, so the relative will give shape here. 10, 20, 30, 40, 50, 60, 70, 80, 90, something like this, 110%. M by Z value, M by Z value here, and the relative potential here. Okay. So in the case of M by Z, methanol, combined with high electron energy, so we got molecular ion 32, we got here, 31, 32, okay, 32 here, slightly not higher, okay, this is 32, M by 32, and then we have 31 the highest, 31, and then okay, 29, have also 29 here, 29 slightly here, okay, 29, and then I can have 15, then 15 here, okay. So here M by Z equal to 15, and M by Z equal to the 29, M by Z equal to 31, and here M by Z 32. Okay. So we have, so this is the mass fragment ion. These are the fragment ions, and this is the molecular ion peak. So here molecular ion peak is not the base peak. The base peak is the M minus 1, M minus 1. Okay, this is the base peak, highest one. Okay. So this is the mass spectrum. So base peak is the having the highest relative abundance, highest intensity. You can say highest peak, and so the base peak here is not the molecular ion peak. So this is about the mass spectrum of methanol. Now let's come to how the different modes of fermentation, how fermentation takes place. So let's see how the fermentation takes place in the. So let's say most of fermentations to give the fragment ions. Fragmentation, okay. most of fermentation to get the pigment ions. So there are many pigment ions can undergo this molecular ion can undergo pigment to give many different types of fermentation. So first one, so I mean molecular ion can undergo these total ions or pigment ions. You can write this way, or you can write this is a molecular ion or bombard which you can give total ions, or you can write M2 neutral, or you can write M1 positive charge plus M2 radical. Okay, so these are total ions. They can undergo further fermentations bombarded. So how it is these pigment ions are, these are pigment ions, how these pigment ions are formed by these things. So I will write down here. First one is the fermentation. Most of fermentation are there. First one is loss of, or you can say fermentation at the branching point. Fermentation at the branching point. So most generally for the branching point. Okay, this is generally found in the hydrocarbons. Okay, long chain hydrocarbons branch with a branching system. So here I can say fermentation adjacent to the at the branching point, or you can say fermentation, or you can write fermentation adjacent to the branching point, adjacent to the branching point. Okay, generally, so here, so let's say this compound. Okay, this is the, so here let's say hydrogen, or hydrogen here, or here, some other branching point here, and then we have another hydrogen like this. Then here fermentation takes place in here only. Okay, not here, because of mostly my fermentation generally takes place in the with a higher branching point. I mean higher molecule will not be given, ferment will not be given. The go fermentation as this is the movement of the electrons. When electrons bombarded with electrons, generally lower molecular mass or molecular fraction, lower fraction will undergo fermentation. Lower fraction will undergo fermentations. So we can show here branching takes place. So here, suppose here, so in the branching point, adjacent to the branching point, fermentation takes place. In this case, so fermentation takes place at the lower fraction. Okay, not in the higher fraction, not in the higher fraction type. So this one will give the, so this will give the higher fraction will give here. So this will give the branching point. So I'm repeating again. So in the long chain hydrocarbons having branching system, the fermentation at the branching point takes place. So here mostly it is fermentations of the longer group fermentation of the fraction having the higher mass, or you can say higher fraction will go ahead. You can what will give it here also, but the base peak fermentation can give here or here, but the base peak and higher intensity will be the one base peak, or you can say higher intensity one will be the one where fermentation takes place with a longer fraction. Okay, so here we can have this fraction. Let's say C is hydrogen here, and here. Okay, this will be this fraction takes here. So with a long fraction. So then this will be the will have high intensity base peak as compared. Here also can take place another fermentation, or then another one. So CH2, CC. Okay, CC. Yeah, so CC. Okay, another one. So you compare these two ions. Here, this will be the by the value of this will be the base peak. So what I'm telling that fermentation can take place at the branching point, but among the branching point fermentation, the ferment ions which is given by due to fermentation, due to the higher fraction will get the high intensity. So this will be the high intensity, less intensity. So we can compare this with the fermentation at the bouncing point. Can compare say by taking one molecule. Okay, you see 2-pentanone and 3-pentanone, 3-pentane or 3-methyl pentane. Another one is 2-methyl pentane. Okay, I'm going to compare by comparing these two. So 3-methyl pentane means CH3, CH2, so here CH3, CH, so CH2, CH3, 1, 2, 3, 4, 5. So this is 3-methyl pentane. Another one is CH3, CH2, CH2, CH3, CH3. Can you see this one? Okay. So here 1, 2, 2-methyl pentane. This is 2-methyl pentane. This is 1, 2, 3-methyl pentane. 1, 2, 3. So here 1, 2. Okay. So we can compare this. They have the same molecular mass and some M by Z value. So we can some can have some permanent ions. So in the case, so here let's say here when you bombard with this, you got a CH3, CH2, CH. First we get this molecular ion. Okay, molecular ion. Then undergo fermentation. So here these are same. Here in this case these are same. So you can undergo here. So you can have CH3, CH2, CH3. Okay, here one electron goes this way. So you can be positive charge plus CH2, CH3. Okay, helical. Then again, you can undergo here also same case. Then again, this can undergo further fermentations. So you can give CH3 will leave, and this will give, this also will fraction. So here fermentation can go here, and then fermentation will go, 2 will go. So you have more ferment ions will give. So you can have ferment ion CH3 positive charge, then C2H5 positive charge. Okay, then this is C3, then another one C3H7 positive charge, and this is C4, this is C4H9. So this is C4H9. Then again, just like this, we can have an M by Z is this one. So this is molecular mass of these simple molecules. 3-methyl pentane is around 86, is 86 molecular mass 86, and by the value of this molecular ion is also M by 86. So here fermentation takes place. So you got C4H9, C4H9. So here keep the fermentation here, the bouncing point takes place. So here this molecular mass is 57. This is M by Z 15, and M by Z 29, okay, 29, M by Z is 43, okay, 43. So you can go fermentation like this, many way, so many fermentations can be formed. So this is about the fermentation in the case of methyl pentane. So you got a big peaks at here. This becomes a base peak in the case of 3-methyl pentane. But similarly in 2-methyl pentane also I can show you 2-methyl pentane. Can show you the fermentation, how it goes the fermentation. It's okay. 2-methyl pentane like this. CH3, CH2, CH2, CH3. 1, 2, 3, 4, 5. Okay. So here fermentation takes place here in this case. So here this is, let's say this is the one. This is the nuclear molecule 2-methyl pentane bombarded with electrons. So you got a CH3, CH2, CH2, CH3. Then you got this molecular ion. Then undergo fermentation here. So here fermentation takes place here. So you got this CH3, CH3. So this is C3, C3H7. So M by the value is 43. Okay, 36 plus 7. Okay. Yeah. So here fermentation can also take place here. So we got another fermentation, CH3, CH2, CH2, CH, CH3. 1, 2, 3, 4. No. 1, 2, 3, 4, 5, 6. We got it. Okay. So here how many are there? C5. No, there's something wrong here. No, this is wrong. 1, 2, C3, H7. So here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so what is value? So here here in this case permutation takes place here. Okay, loss here you got a positive charge here. The another one can loss here also. Another one C this can be lost, and this can be lost, this can be lost, this can be lost. So you can like the earlier one, you can have CH3, CH2 positive charge and CH3 positive charge. So all fermentation. So here M by Z, here uh, 5 by C5H9, C4H9. Here like this, you can have many permutation can take place. Okay, C2H5, then you can have C2H5. So here M by Z 71, 1, 2, 3, 4, 5, okay, 60, 60, 1, 2, 4, 5, 71, like this, and this. So many you can have. Okay, this is 15 M by Z 15, and M by Z 29, like the other cases. So you can get so many fermentations like this. So only fermentation different is that here the M by Z value will be highest will be the metastable here. Base peak will be the this is the base peak. Other case is 57, but here is base peak is 49, 43 here. So in the case of 3-methyl pentane, what I'm doing said, base peak is 57, and the case of 2-methyl pentane, base peak is 43, because the fermentation takes place here this one. So here longer chain cannot, and longer fraction doesn't take place. It doesn't give the longer fraction doesn't give the base peak. So because of the movement of the ions, when it clip is easier here as compared to here. So I will give the mass spectrum of this two. Okay, let us compare how the mass spectrum takes place. So mass spectrum of 3-methyl pentane and 2-methyl pentane. Okay. So here mass spectrum of, so you can have the mass spectrum. So this is 0 to 100. Okay, relative evidence, and this is the M by Z. M by Z value ordinate, and this is ordinate SSR. So you can have 20, 10. So nearly 100. Okay, let's 100. 86 is the best pick. Okay, so here 20, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, then you can say 20, 40, 60, 80, 100. Okay, 86 is the molecular peak is very small. But in the case of 2-methyl pentane, this is 43. 43 is the 1, 2, 3. 43 is the base peak for 2-methyl pentane. So M by Z 43. And the other case 15 here, you can have then 15 C3, M by Z value is 15, and another C2 is 5 is 29, 20, 30, 29 is like higher. C2 is 5, positive charge is 29, M by Z value is 29, M by Z value is 15, and here is M by Z is 43, is C3 is 7, C3 is 7, the fermentation is the highest, the fermentation is highest one. Another one is C4H9 57, 57. So here C4H9 with the charge, and then again another one 71, 71. Here C5H11. Okay, positive charge, and by that value is 71, is 57, like this. So here it is about a 2-methyl pentane, okay, pentane. But in the case of um, 3-methyl pentane, it is slightly different. So fermentation will be not the best. This is not the best peak. In the case here, it is the case is best peak is this one. Okay, fermentation takes place here. Here is test CH3. Fermentation takes place. Okay, here. So you got this best peak. But in the case of the 3-methyl pentane, in the case of 3-methyl pentane, you can say CH3, 1, 2, 3, okay. So fermentation either going this way or this way. So you got this C4 is C4 H9, mean 1, 2, 3, 4, H9. So this is C3 H7. Okay, this is 1, 2, 3, 4, C4 H9. So this will be here in the case, this is for 2-methyl pentane. And similarly, in the case of 3-methyl pentane, you can have this 3-methyl pentane. The base peak will be here, high intensity. So C4 is 9. Okay. So here this is C3 is 7. Okay. So I'm showing here for 3-methyl pentane. So by seeing the base peak value, so we can say which one is which one. So if it is the base peak is C3H7, then you can say 2-methyl pentane. If it is base peak is C4H7, then this is 3-methyl pentane. This way, so method of fermentation takes place at the branching point. So what I'm telling. And the second one is fermentation is by loss of small molecules. So by loss of fermentation, second one is fermentation due to by loss of simple molecules. All neutral, okay. So fermentation due to loss of, you can say fermentation due to loss of small molecules. So small molecules like small stable molecules like water, carbon monoxide, carbon dioxide, or you can say nitrogen ammonia, and then from the ammonia from the amines, CH, triple bond CH, CH2, double bond CH2, all these are etc. So small stable molecules like water, carbon dioxide, and ammonia, ethylene, etc. can be lost by fermentation ion. Okay, so suppose from alcohol, this is alcohol. Okay, let's say R here. So fermentation is a bombarded with molecule. Then you got a molecular ion. Then you can lose water. You can lose water. Then you can have molecular ion. This molecular ion P, loss of water. So you can have M minus water. This okay. What is another one peak prominent peak. So you can say M minus 18 peak. So these are very prominent peak. So you can say it is a base peak. So I'm giving one example. Similarly, you can say ammonia NH2. And then from amines you can lose ammonia, then like this. So we also what is that fermentation can due to loss of small molecules can also take place. This is the second one. Fermentation due to loss of small molecules. And third one is fermentation to keep stable carbocation. Third one is fermentation to give stable carbocation. Okay. So the fermentation takes place at the point where to get the most stable carbocation. For example, I will give here. This common fermentation like this. This is RSA enzyme. Okay, this is one molecule bombarded with electrons. So we got this one molecular ion, molecular M plus ion, molecular M peak. So this one undergo fermentations to lose this one. This will be radical So you got a R radical plus this CH2 positive charge. So you can undergo many resonance structures. So many resonance structures. These double bonds can give, or like this also can give, expand the ring. So you gotta have seven member ring. So you can have this one, all can be positive charge. So you can add tropylium ion. This is very tropylium ion. It's very stable, so you can get stable carbon yes, because this is primary, so you get a so lost this one, you can get a positive charge here. Okay, so this way this positive charge can be delocalized again. So many structure comes. So more resonance structures, more stable. Carbocation is more stable. So these permanent ions will give the highest peak, highest intensity. So what I'm telling that fermentation takes place to give the more stable carbocation. And the fourth one is fermentation due to due to movement of one electron. Number four, fermentation. Fermentation takes place by movement of by movement of one electron. One electron. This is free radical type one electron. So here, for example, say let's say this is a neutral molecules bombarded. Then we got a molecular ion, parent ion. They undergo say fermentation. So one will give like this, other one only. So here I write down. Okay, here. So let's say pass one. This one electron go to another one, and then similarly you can have another example. Say CH3, CH3. So really long chain and CH3. So this molecular ion after bombarded. So here fermentation will go this one like this. So you get R, and then this long. This is the permanent ions positive charge. So this is the branching point. So it may be long chain. So it, one electron, one electron moves like this. So this is movement of one electrons. And second is third, fourth. Another one is, so you can have this one. We have. So you can find this one also. Fermentation. You can in the other case also like alcohol, say like fast alcohol is bombarded. So like this. So you can have lose this one. So let's say CH R. Okay. So one electron here moves, another one single electron. So this way, another one this way. So you can have this another one like this. So like this. So here one electron movement takes place. So this is a molecular. So ion can take place movement by fermentation can take place by movement. So you want the hydrogen has gone. So you got like this. Or you can this one's R also go like this. So fermentation takes place by movement of one electron. One electron movement is represented by one free soup. Okay, this electron, one electron, and this full layer wise two electrons are movement. So here I will keep repeating again. Another one is fermentation by movement of two electrons. One is fermentation by movement of two electrons. This is very common. Okay, two electrons. This is very common. And fermentation by movement of one electrons are generally take place by say by heating by light or UV lamp also. This one by light. Okay, but here heating decomposition takes place by two electrons. Okay. So it is two electrons very common. Say what two electrons in the case two electrons are moved by this full arrow. Okay. And then other one fermentation due to by multiple. So here, I'll give you example one here. For this example, I'll give okay. Say R O R. This is let's say ether. Then the loss of this ferment this one you can have bombardment with electron. This will give say positive or okay this is ether. So why two electrons are moving here, two electrons are moved. So you got R positive charge cation comes and this become O R. So electron. Okay, this is radicals. Okay, it comes radical OR radical. Okay, so like this. So my movement, two electrons are movement. So I'm giving examples. So many examples are here, and it's very common. Okay. Then we have 6-1 elimination, fermentation due to the due to the top 6-1 fermentation due to the elimination of 6-1 due to the elimination fermentation due to elimination by fermentation due to elimination by multiple sigma bonds. Okay, this is generally found in the electrolysis reactions. Say for example, this type of compound. Okay, let's say this one. Okay, so here bombarded electrons, one electron loss. So you can have this one molecular ion. Okay. Then you can have by two electrons you can go, this fragmentation can take place this way, this one like this. So fragmentation take place. So here is double bond will come, and double bond will come here. So this is plus, this is here. Okay, so this is two electron movement takes place. But you can similarly you can have also this one can have single electron. Okay, this is molecular ion, this one. So you can have single electron movement can take place. So this one and this one and this one, single electron. I'm telling that this one goes, that is double bond, and this also gives double bond, and the other one like this. So it is same product. Okay, but here one electron movement and two electron. So here fermentation takes place due to this. So this today we will take up this. Okay, up to this much. Next class I will take more. I will continue the different modes of fermentation. Next class also, and then will come negative 40 and then nitrogen will like gas. So up to this today we'll finish here. So I'm just summarizing. Okay, about classes we have done. So in the summarizing this thing, so principle of mass spectrometry is that the basis of mass spectrometry is that the bombardment of high energy electrons to the nuclear molecules to give fragment ions, then subsequent fragment fermentation takes place and to give the fragment ions. So by studying these molecular ions, fragment ions, we know the structure of the compounds. So it's a study of this decomposition of the nuclear species to give ions, and subsequent fermentation of these ions is the basis of mass spectrometry, a principle. So I am giving example, for example, how benzene when comparative electrons, one loss is no out, so you can one electron is no out, so get the cation radicals, and electron can capture by the nuclear species, so you get the cation radical. But generally in mass spectrometry, cation radicals are studied. So we have examples are given, and mass spectrum we studied mass to Z ratio, the mass to charge ratio is SSR, and relative abundance in the ordinate is gives the graph gives the mass spectrum of the compound. So I'm giving different modes of fermentation. First one is fermentation adjacent to the branching point, and second one is fermentation by loss of due to the loss of small molecules. So I'm giving example also. Then we have fermentation due to movement of one electron, fermentation due to movement of two electrons, fermentation to give the more stable carbocation, and we have the lastly we have fermentation due to elimination of multiple bonds, sigma bonds. So my sigma bonds are clipped here. So two sigma bonds are clipped. So we got this compound. So this is retro-Diels reactions. So this is too much today. We will do to next class we will do other. Okay, thank you. Next class we will